So, welcome again to the course Fundamentals of Solar Photovoltaics and Technologies. Today we are in lecture 10. Here again we will continue our discussion on the basics of semiconductors, that is what leads to formation of bands in the materials. So, just to recap, what we did in the last class was we first learnt about free electron theory, which is based on quantum mechanical principles to explain the behavior of electrons in the crystals. Electron is considered to have dual behavior, that is, it can act like a wave and like a particle simultaneously, which is given by de Broglie, and based on this we showed an equation which was predicted by Erwin Schrödinger, that was Schrödinger's equation, which combines the potential energy and kinetic energy of electron in a given situation. So, we solve this equation under few boundary conditions. So, electron without any boundary conditions and there is no potential applied, it can have any energy. So, without any boundary condition and without any potential. Can have any energy. So, that was showed, you can have a curve like this EK diagram, and basically it can achieve any energy as it wants. Then we looked at the free electron model for electron in a potential well in a crystal. We looked at two cases, one was finite potential, second was infinite potentials, and we solved the Schrödinger equation using the periodic boundary conditions, that is psi r plus L is equal to psi r, and that this wave function is continuous and its derivative is also continuous. And what we get in a solution in a infinite potential is that there are discrete energy levels for electron in a box or in a crystal. So, this lays the background for quantization of energy. So, electron cannot have any energy, it has to follow, it can only occupy certain energy states, and whose expression was E is equal to n square pi square h cross square divided by 2 m l square. When atoms are brought together, the wave function of these materials overlap. So, wave functions of electrons overlap, and hence energy continuum may exist, but with discrete energy level. And so, what we see is that we have, in many electron system, we have many energy states. So, up to the Fermi level we can have as many as 10 to the power 23 states. So, the gap between each of these is 10 to the power 23. So, you can say 10 to the power 23 atoms. So, gap between each of these is approximately 10 to the power minus 23 electron volts. So, they are in some sense continuous, but each of these energy levels is discrete. And as we will see today, the crystals show formation of bands. So, in addition to quantization of energy, they show bands. So, what we did was A and B, that A is about the bound electrons, for example in large potential, which show quantized energy levels. B is for free electrons which are not bound, which can occupy any energy, and C is what we get for materials, that is how do electrons in a solid behave in a lattice with finite potential. Now, there is a lot of quantum mechanics involved in here. There is a concept of reciprocal lattice, there is a concept of Bloch theorem, a lot of those theoretical background needs to be done, and we do not have time to go through that, but I would recommend you to go through electronic properties of materials. The early chapters in this book, they will give you a sufficiently good background into quantum mechanical aspects, but basically these quantum mechanical considerations and interaction of electron with the lattice leads to certain conditions which lead to formation of these bands. So, electrons, basically any solid does not contain just one electron, there are many electrons, and solid has a periodicity. So, each solid is characterized by presence of unit cells, and there are multiple unit cells in a solid per unit volume, and what we see is energy bands in crystals. So, basically if you look at electron, if you look at a 1D lattice, so 1D lattice, these Z ones are atomic cores, and around these cores we have the potential around the ionic cores and electron. So, we can say that each of these region, So, each of these region is equivalent to the any other region in the lattice. So, this is a repeatable region. So, this is one part of lattice, which is, let us say, a unit cell, and this unit cell is periodic. So, whether so a potential at any given point V r plus r is equal to V r. So, r is the lattice translation vector. So, if you translate anything in the lattice by lattice translation vector r. So, capital R is lattice translation vector. So, if you translate potential by this vector in the lattice, you will see identical situation at that position also. So, that is why all the calculations that we do are for one unit cell, and this unit cell will give you the answer. Another thing that we need to consider, we know that K is called as wave vector, which is the wave vector for electron, and its unit is basically 2 pi by lambda. So, lambda is in meter. So, the magnitude of K will be in meter inverse. So, electron with a wave vector K interacts with a lattice. Real lattice has a lattice vector R, as I told you earlier. The analogous reciprocal counterpart of lattice is called as reciprocal lattice, and this reciprocal lattice vector is G, which is basically in the reciprocal space. So, R can be written as N1 A1 plus N2 A2 plus N3 A3, a lattice vector in A1 A2 A3 axis with N1 N2 N3 translations. G on the other hand can be written as M1 B1 plus M2 B2 plus M3 B3. And here B1, B2, B3 are reciprocal lattice vectors. So, B1 is a reciprocal lattice vector, which is written as 2 pi divided by A into B. So, let us look at what is this lattice translation vector. So, for any given lattice, let us say here we have plotted a face centered cubic lattice. Here we say that the lattice translation vector is N1 A1 plus N2 A2 plus N3 A3. And face centered cubic lattice is a non-primitive lattice, which means it contains more than one lattice points. The primitive lattice vectors for this lattice are A1 A divided by 2 y plus z, A2 is A2 z plus x, A divided by 2 z plus x, and A3 is A divided by 2 x plus y. And using these vectors, one can create a primitive cell. So, primitive cell is the one which contains only one lattice point. So, I assume you know what is a primitive cell. So, this is the smallest primitive cell that we find inside it. This can be constructed in a different manner also by creating a Wigner-Seitz cell, which is essentially, if you take let us say a lattice like this, then one way to create cell is to create a unit cell like this. This is a primitive cell, but alternative way to create a primitive unit cell is to draw the perpendicular bisectors. So, first draw the perpendiculars to the connectors to the nearest neighbors, then draw the perpendicular bisectors to these, and then draw the cell around it. So, if you draw the cell will be this. So, this is also a primitive cell. It only contains one lattice point, but this is called as Wigner-Seitz cell. So, again it is a primitive cell. Now, the lattice point is inside it rather than being at the corners of this cell. So, basically this is a primitive cell in real space. The reciprocal analog of this is called as reciprocal lattice vector, which is given as G, and G is M1 B1 plus M2 B2 plus M3 B3, where V1 is 2 pi into A2 cross A3 divided by Vp, which is Vp is volume of primitive cell, which is A1 dot A2 cross A3. B2 is 2 pi A3 cross A1 divided by Vp, and B3 is 2 pi A1 cross A2 divided by Vp. And by the periodicity of the lattice, the relation, this relation should always uphold, that is e to the power I g dot r plus r is equal to e to the power I g r plus r, because g is perpendicular to r. As a result, the dot product of these will be equal to, so e to the power I g dot r will be equal to 1, capital R will be equal to 1. So, reciprocal lattice basically is representation of the Fourier transform of the special wave function of direct lattice, and reciprocal lattice can be defined by the set of all g vectors which satisfy this identity, the one which is written here, exponential I g dot capital R plus a small r plus is equal to exponential I g dot small r, where capital R is the direct lattice vector, capital G is the reciprocal lattice vector, and R is any translation, any point in the coordinates of any point in the space. So, R is a given position. So, basically a reciprocal lattice is Fourier transform of real lattice, and real lattice is inverse Fourier transform of reciprocal lattice. So, basically why did we invoke this? Because when we talk about wave is characterized by wave vector, which is k, which is a reciprocal quantity, and this interacts with the lattice. So, this is electron wave. Okay. So, reciprocal lattice, we have reciprocal lattice vector G. So, these two quantities, they can be, so one can look at the interaction of electron with the lattice in reciprocal space, and that is why the concepts of reciprocal wave vector and reciprocal wave vector which is in reciprocal space and the reciprocal lattice vector are invoked. So, once you look at this and the primitive cell in reciprocal space, which is the Wigner-Seitz cell in reciprocal space, is called as Brillouin zone. So, basically it is the interaction of electrons with the reciprocal lattice which gives you certain phenomena at the boundaries of Brillouin zone, which leads to creation of these energy bands. So, I will not go through details of that. Essentially what happens is that if you plot EK diagram, the EK diagram for a normal if you do not apply those conditions, EK diagram will be like this. Okay. This is your EK diagram, which is E is equal to h cross square k square divided by 2m. Okay. Now, for quantum mechanical reasons, the electrons undergo diffraction at the reciprocal lattice points or at the boundaries of Brillouin zones, and boundaries of Brillouin zones are characterized by these points. These are reciprocal points. So, this is plotted as Ka. So, if you just plot it in terms of k, then it is pi by a, it is 2 pi by a, it is 3 pi by a, 4 pi by a. These are, if you plot in terms of k, these are called as reciprocal lattice. These are called as lattice points at the boundary of Brillouin zones. So, this is the boundary of first Brillouin zone, this is the boundary of second Brillouin zone, this is the boundary of third Brillouin zone, this is the boundary of fourth Brillouin zone, and because of quantum mechanical reasons, it is at this point this gap starts appearing. So, the curve sort of breaks, curve splits into two parts at this point, and what is on the y axis? Y axis is nothing but energy. So, basically energy at this point splits in two half with a gap. So, you can see that at this point we have a gap, this is a gap, this is a gap, this is a gap, and we have energy states like E minus, this is E plus, this is again E minus, this is E plus, this is again E minus, this is again E plus. So, if you now plot it schematically it will look like this. You have first band, this is band 1, which let us say is this, which is separated by second band like this. This is a gap, this is band 2, and let us say if I do not use the red color just to avoid the confusion, I can plot it using first band, this is second band, and then followed by this you will have another band which is third band, something like that. This is band 3, again we have a gap, and then again we have a band. So, this is for quantum mechanical reasons, because electron undergoes a phenomena called as diffraction. So, electron undergoes diffraction at these reciprocal lattice vectors. Okay, and this is, so this causes splitting of energy levels. So, we have basically it causes wave function to have a standing wave solution. As a result, you have two solutions of wave function. So, this I will explain that in the next few slides. So, basically because of periodicity of because of EK periodicity, because if you plot this EK diagram across the whole Brillouin zone. So, this has been plotted across the, so this is your EK diagram for just one zone for Kx, and if I plot the EK diagram across the whole Kx space, that is the reciprocal space, this is reciprocal space. And this is energy. You can see these, so this is the central curve, and these curves keep shifting at different lattice points. You can see they are all identical. So, if I just operate within this region, this is the region I operate in. Everything is identical, in different regions. So, we can just operate within first Brillouin zone. So, everything has a periodicity of this. So, we do not need to look at a second unit cell, we can just operate in one unit cell of reciprocal lattice. So, because of periodicity of energy wave vector diagram or EK diagram, all the information about materials one can obtain from the first Brillouin zone itself. So, this is, so first Brillouin zone will be from minus pi by a to plus pi by a, this is minus pi by a, this is plus pi by a. So, this is the first Brillouin zone that we have. So, we can obtain the information only from this zone. We do not need to, because everything else is identical in any other zone, because as I said, psi at r plus r is equal to psi at r, and this is the lattice translation vector. Similarly, in reciprocal space also this follows, and any wave vector k prime is also equal to k plus g. So, if you translate any wave vector with g, they are all identical. So, any k primes at a distance g from k is identical to k. This is because of periodicity of lattice. So, basically energy E k prime for any k prime vector which is outside the first zone is identical to the energy E k within the first zone, if you can find a suitable translation vector g, and there are always these suitable translation vectors available. So, this is what we are interested in, this first Brillouin zone. So, if you apply these diffraction conditions across the whole space, you get a EK diagram like this. This is just in 1D for a 1D crystal, not for a real crystal, but for a 1D crystal you get something like this. So, you can see that, so this was your initial diagram, EK diagram. And your first Brillouin zone will be only, this will be the first Brillouin zone. You can see that this part is identical to any other part in the crystal. So, you do not have to look at anywhere else, and you can now see there are these tiny gaps which are created in the diagram. So, you can see that there are tiny gaps, there is a gap, tiny gap here, there is a gap there is a gap here, there is a gap here. So, you create these gaps within the crystal, and these gaps are essentially your band gaps as we call them. So, you create basically first a N band, then a M band and other bands, and initially the gap is very small. You can see this is the tiny gap, but then this magnitude of this gap keeps increasing. So, this is also gap, this is also gap, this is also gap. Depending upon material to material, some material may be filled up to this level. If it is filled up to this level, then it will have different electronic characteristic, but if it is filled up to this level and empty beyond that level, then it will have different electronic characteristics, and we will see that later on. So, basically because of periodicity of lattice, all the information we can obtain within the first Brillouin zone. We do not have to worry about higher Brillouin zones, and any energy E k prime for a vector k prime outside the first zone is identical to the energy within the first zone if you can find the suitable translation vector G. And this is how the band is going to look like. You have gaps like these. So, you have these different band gaps. So, this will be the gap here, that is the gap here, and within this you have states. And if you plot this in a scalar, this is basically N band, M band and higher number of bands. So, and that is how it is going to look like for a real material. So, basically free electron in an empty lattice acts like that, and when you apply the periodic potential, when you put that electron in a lattice with a periodic potential, then we create these splitting of energy levels at the boundary of the Brillouin zones, and this gives rise to gap states in the EK diagram. Of course, this is a treatment for 1D material. You can do similar treatment which is far more complicated for materials in general to determine EK diagrams in 3D lattice with periodic potential. So, for this I will refer to solid state physics, Charles Kittel, or electronic properties of materials, by R. E. Hummel. These are the two good books which can give you a better insight or detailed insight into what we have just talked about. So, essentially this is what it looks like. You have a EK diagram. At the boundaries of Brillouin zones we create the gaps, and we can translate these higher order diagrams into the first order. So, in 1D the Bragg condition will be at, so Bragg condition is the diffraction condition, we call it diffraction condition. So, diffraction condition means that small k has to be equal to half of plus minus capital K, which is plus minus n pi by a. So, n is equal to 1, 2, 3, so on and so forth. So, you can say k, small k will be equal to plus or minus pi by a, plus or minus 2 pi by a, and so these are the boundaries of Brillouin zones. This is where diffraction happens. So, these are boundaries of Brillouin zones, and this is where diffraction happens. So, at the boundary of this Brillouin zone, electron undergoes diffraction as we talked about, and it results in a standing wave solution of the wave function. So, you have a psi plus and psi minus. Corresponding to psi minus and psi plus, we have we create because of this we get two energy states. So, we get E plus and E minus, and the difference between E plus and E minus, which you can find out, is the Eg, the band gap, and we can write this Eg as minus 1 to plus 1 Vx psi plus square minus psi minus square integrated over dx. So, this is just for 1D. In 2D it will be far more complicated. So, this is nothing but your Eg is equal to E plus minus E minus. Okay. This is what you get, and you can translate these into first Brillouin zone. You can translate these, this is identical, you can translate this to that, and these are translations into first Brillouin zone. So anything in higher order Brillouin zone appears similar to first Brillouin zone. So this is basically how you create the bands, and because of periodicity of lattice, everything in first Brillouin zone is similar to higher Brillouin zones. So now you understand that bound electrons, the free electrons give you, when your potential is 0, they give you energy continuum. The electrons can occupy any state. When you have bound electrons, when they are in a potential let us say V is equal to infinity, then you have quantization of energy. So you have E1, E2, E3, E4, E5, E6. But when you put electrons in a solid in a periodic potential, then we get the creation of these bands. So we have band 1, so there is a tiny band here, so this is band 1, this is band 2, this is band 3, band 4, and between these bands we have what we call as gaps. So early bands are very, very thin, so that is why you just see them as thin lines, but they are actually bands. So this is band 0, let us say the ground level band. Okay. So we will stop here. In this lecture we have tried to explain how the bands form in the materials, which form by interaction of electron with the lattice and electron undergoing diffraction in the lattice at the boundary of first Brillouin zone, and at those points the energy state splits into two. So because of standing wave solution of the wave, electron wave, and we create two functions for psi plus and psi minus, two wave functions. Correspondingly we will have E plus and E minus two energy states, and the difference between those two energy states is the gap, and this gap continues from lower energy to, and formation of these bands and the gaps between them continues until the higher energy. And in the next class we see how do they look like for real materials, things like silicon, gallium arsenide, germanium, and also for metals, and how do metals and semiconductors behave in a different manner. Okay, we will do that in next class. Thank you.